Hey, this is Joe, and today let's talk about the constant of integration. And that is, when I have an indefinite integral, an integral that's not bounded, and you take that integral or antiderivative, we're told to add c to represent a constant of integration. So where does this c come from? Let's start by taking the derivative of a few functions first. Say I'm supposed to take the derivative with respect to x of x to the fourth plus 3, of x to the fourth plus 20, and of x to the fourth minus 4. And to take the derivative of these functions, we're going to use the power rule. And if you need a refresher on that, you can check out this video here. So let's focus on taking the derivative with respect to x of x to the fourth plus 3. To take the derivative of x to the fourth, we bring the power out front of the variable, so we get 4x, and then raise it to the 4 minus 1 power, which will be 3. And then, when we take the derivative of the constant 3, we're told that the derivative of any constant is equal to 0, so that's going to be 0. So the derivative with respect to x of x to the fourth plus 3 is going to be 4x to the third plus 0, and we can drop off that 0. Now, if we look at these other two derivatives, we're going to end up getting the exact same result. We're going to get 4x to the third for all three of these, and the constants are all going to disappear. So what we've done so far is taking a derivative. So if we're going to take the integral of the result or the antiderivative of 4x to the third, we should get back towards our original functions. So let's take the integral of 4x to the third dx. We're going to use the integration power rule or the antiderivative power rule, and you can check out a refresher right here. Within that rule, we're told to take the power of the variable and add 1 to it. So we take x and raise it to the fourth power, and we divide by that new power. So we get 4x to the fourth over 4. And we can cancel out the 4's, and we just have x to the fourth here. But recall, all three of our examples that we started with had a constant attached to them. And when we go backwards, or when we take the antiderivative of our result, we have no way to match it up to the 3, the 20, or the negative 4. So we add this c to represent all the potential solutions that we could have for the resultant function of the indefinite integral. So now let's move on to an example where we end up solving for c. Say we're told that capital F of x is equal to the integral of 3x squared dx, and then we're told that capital F of 1 is equal to 4, and we have to find capital F of x. Capital F of 1 equals 4 is a solution to capital F of x, and it is useful to help us solve for c once we take the indefinite integral. So to solve for capital F of x, we're going to just start by taking the integral of 3x squared dx. 3x squared dx, we'll take the power of x, we'll add 1, and then we're going to divide by that new power. So 2 plus 1 is 3, and we're going to divide by 3. We add c because we don't know what constant we may have missed during the integration. We can cancel out the 3's and we just get x to the third plus c. So far what we have is capital F of x is equal to x to the third plus c. So now we can use capital F of 1 equals 4 in order to find the correct value of c for capital F of x. We use capital F of 1 equals 4 by plugging 1 in for x and then solving for c. So we plug 1 in for x, so we get capital F of 1 equals 1 to the third plus c. Since capital F of 1 is equal to 4, we can replace this left side with 4. So we get 4 equals 1, since 1 to the third is 1, plus c. And then to get c by itself on the right side, we're going to subtract 1 from both sides, and we end up getting 3 equals c. This tells us that we can replace c within capital F of x with 3. So we could have capital F of x equals x to the third plus 3. Now, for a quick recap, we add c to the result of any indefinite single integral to represent any constant that could be lost during that derivative and integration process. In order to then solve for c, we have to be given some initial value or solution to our resulting function, our capital F of x. And that initial solution will have the form of capital F of some value of x is going to be equal to some constant. So some examples would be, say, capital F of 3 equals 5, or capital F of 2 equals 80. We then plug the initial solution into capital F of x and solve for c. So hopefully you kind of understand what this plus c represents within integration. I'm Joe, and thanks for spending some time with me.